So the last speaker for this session is Agniv, and he would be talking about best arm identification in multi-armed bandits.
Shall I start? This is joint work with Sandeep Juneja, Kartikeya Shanmugam, and Arun Sai Sugala. The problem is about best arm identification in multi-arm bandits with offline data. So what the best arm identification problem is that there are k unknown distributions, and we can choose one of these. So they're also called arms, and we can choose one of these arms at a time and see a sample from there. We want to determine the distribution that has the maximum mean, that's the best arm, with a probability of error at most delta. And in the process, we want to collect the minimum number of samples. And so this is the classical best arm identification problem. But what we also have here is that there are a lot of offline samples for every arm, and for a given delta, the offline samples kind of scale linearly with log 1 over delta with some constant. So some assumptions. So we assume that all these distributions or arms are from some single parameter exponential family, and so they can be parameterized using only their mean. In this setup, we want to design something called a delta correct algorithm, which is the algorithm takes a delta as an input, and it must, and for every delta and instance, it must give me the best arm with correctly with a probability at least 1 minus delta. And we want to design a delta correct algorithm which takes in this offline samples and which also consumes the minimum number of online samples in the process. Offline samples. So what we know about offline samples is that for every arm, the number of offline samples is some constant times log 1 over delta. And we know that constant because we can see the number of offline samples and just measure that constant. Yeah. So you can think like a Gaussian, so all Gaussian distributions with some constant variance. So you can see, right, like they can be parameterized using their mean only. Also, Barnoul is our SPF. All right. Now we want to design an algorithm that consumes the minimum number of samples, and that takes us to the lower bound problem. And so using data processing inequality, we can show that for every instance, so here instance means the distributions and the number of offline samples. For every instance, the number of samples that I need is lower bounded by the solution of this problem O1. And what O1 does is we want to collect the minimum number of samples such that for every arm, the number of samples must be at least the number of offline samples. And for every suboptimal arm, we want this quantity, and this we call the index, to be larger than log 1 over delta. And what the index means is it means the amount of evidence we collect for each of these suboptimal arms. And we want that to exceed log 1 over delta and take the allocation which minimizes the overall sample complexity. Now one question is like, how do we, so how does the solution to this problem look like? And it appears that, so for any instance, the solution to O1 is of the form T star times log 1 over delta. And this T star is a function of the instance. Like for every instance, there is a constant T star, and the lower bound is this T star times log 1 over delta. And we call an algorithm asymptotically optimal if as delta goes to 0, the overall sample complexity is less than T star log 1 over delta. And we want to design an algorithm which satisfies this condition. Now, so there are two aspects here. One is like making sure that the algorithm is delta correct, and the other one is asymptotic optimality. Now, for delta correctness, there is an existing result that all we have to do is we have to stop the algorithm when this minimum index exceeds some log 1 over delta plus some smaller ordered terms. And this minimum index is kind of, so as we collect samples, the minimum index increases and it quantifies the amount of evidence I am getting from the samples. And we want to stop when this exceeds log 1 over delta. And this is also called the generalized log likelihood ratio rule, with this minimum index being the GLLR, and it is well known in the literature. Now the question is, so can we allocate samples to different arms in such a way that this minimum index actually increases in the fastest possible rate? And it appears that if we somehow make the allocations which is the optimal solution to the lower bound problem, then this increases at the fastest possible rate and the algorithm becomes asymptotically optimal. And one easy way to do that, like is every time we have these empirical estimates, and we plug in these empirical estimates into the lower bound problem and solve this k variable problem at every iteration, get the optimal allocation, and simply track that optimal allocation. And it is not hard to show that. So this is called the track and stop algorithm, and this is studied in the literature widely. And it is not hard to show that this algorithm is actually asymptotically optimal, because the solution to the lower bound problem behaves like a continuous function of this estimates that we are plugging into it. So the overall allocation converges to the optimal allocation. All right, but so there is a problem with this track and stop, is that at every iteration we need to solve this k variable convex problem, and this k can be very large. So this is like computationally very expensive, and we don't want to do that. And that brings us to something called so one way to bypass this issue is creating something called a top 2 algorithm. And what is done here is at every iteration we maintain 2 arms. One is called the leader, which is like the candidate most likely to be the best arm, and this is the arm with the maximum empirical mean. And the other one is called the challenger, and the challenger is the suboptimal arm, which is most likely to be confused with the best arm, like the suboptimal arm for which we have the least amount of evidence. And typically this is taken as the arm that has the minimum empirical index. So this was the index in the lower bound problem. And we somehow switch between these 2 arms depending on some if-else condition, and stop when the GLLR condition is met. And one simple way to do that is let's toss a coin at every iteration for which head comes with probability beta. This beta can be a constant we plug into the algorithm before at the beginning. And if it gives us head, then we choose the leader. Otherwise, we choose the challenger. And this is studied by this is called the beta top 2 algorithm, and it has been studied by several papers. Like for example, Rusho in 2016 showed that this beta top 2 algorithms are beta asymptotically optimal, and what that means is they are asymptotically optimal, but with the added constraint that we give beta fraction of the overall samples to the best arm. So here, so there is one natural question is like, what is the best beta to plug in the beginning? And for every instance, there is a unique beta which is optimal, and and to make sure that this beta top 2 algorithm has the minimum sample complexity, we need to know that optimal beta beforehand for this to work. So a natural question is there a way to learn this optimal beta with the samples being collected? And so in a previous paper, me with Sandeep and Shubhada, so we designed something called a anchor top 2 algorithm. And what we do here is instead of tossing a coin with a fixed probability of head, we use this weird function. So this we call the anchor function, and this is basically a sum of ratios of scale divergences. And I'll say like how we get this function later. So we use this function called G, and whenever the G is positive, we just pick the best arm. And whenever it is negative, we sample the challenger arm. And we can show that this algorithm is asymptotically optimal. It learns the optimal beta. And the way we get this function G is we have this lower bound problem. So this is a lower bound problem for the purely online setting. And like, see here we have just na greater than equal to 0. So we don't have any offline samples. And when we study the first order conditions of this lower bound problem, we get like the allocation must satisfy that the anchor function is 0, and all these indexes must be equal to log 1 over delta. So by this sampling rule, we try to make sure that the anchor function converges to 0. And the very way we are choosing our challenger, we make sure that the index has become equal over the course of time. And why this anchor function comes is that we kind of reduce this k-dimensional problem to a one-dimensional problem. And this anchor function is the gradient of that one-dimensional problem. And it looks something like this. And so the optimal allocation is just the point where this anchor function becomes 0. And this is a smooth function. So G equal to 0 gives us the optimal allocation. Now the question is, can we do something similar in our offline problem also, where instead of 0, we have a bunch of offline samples for every arm? How much time do I have? 7 minutes. Okay. So that takes us to the first order condition of the lower bound problem with offline samples, and we can see that the similar functions appear in the first order conditions, like this sum of ratios of scale divergences. But I mean, we see this structure that this sum of ratios over some set A1, this must be less than equal to 1, and over another set of arms, A1 union A2, this must be greater than equal to 1. And we get this because when we plug in this offline samples, then instead of getting a smooth convex function, like in that one-dimensional reduction, instead of getting a smooth convex function, we get a piecewise smooth convex function, and that ratio sum appears to be the derivative of this convex function at the points where it is differentiable. And if there is if at the point of the minima it is not differentiable, then we get that condition that in one side the gradient must be negative and in the other side it must be positive. And we want to leverage these conditions to get a appropriate anchor function. So what appears is that we don't have to take the sum of ratios for all the suboptimal arms, but we instead have to take this sum over a subset of the suboptimal arms, and this subset so this subset of suboptimal arms is decided based on this condition. And okay, what this condition basically says is that it kind of predicts what suboptimal arms have insufficient offline samples, and we have to gather more evidence for these arms. And we get this by like reframing rescaling the first order conditions. So we just replace the log 1 over deltas by the minimum index, and and this we call the clairvoyant anchor top 2, because this anchor function has this property that it kind of can foresee which suboptimal arms need online samples later. And based on that, it adds those suboptimal arms before they start getting online samples. To analyze this algorithm, we designed something called the fluid dynamics, and what it does is that what the algorithm is doing is, so you can consider these arms as buckets, and we are adding samples to these buckets, right? And over the course of time, this empirical means are concentrating to their true means. And what we do in the fluid dynamics is, let's say we are not adding granular samples, but we are just pouring some continuous fluid into them, following this clairvoyant anchor top 2 algorithm. Well, let's say the mean of these arms are already known. Then the dynamics of this algorithm can be can be seen as a system of ODs, and there are multiple system of ODs, and they're pasted together. This is something we did in our earlier paper as well. And when we study this dynamics, then it happens that so there is this set B1, and we are only taking the ratio sum over this set. It appears that whenever a new arm gets added to the set B1, and the anchor function G gets a jump, then G starts immediately oscillating between these two values. Like with this arm repeatedly getting added and ejected from the set B1. And why it happens this way is because whenever G gets a jump, this C82, like the algorithm changes from G to this function, and to some proxy anchor function, and uses that instead as an anchor function. And that's why we kind of see these oscillations. And now in this situation, if the algorithm stops, then it does stop in the stopping condition, where this anchor function measured over one subset is less than 1, and over a slightly larger subset with this new arm that just got added, that is greater than 1. And that's how it sort of stops at the first order condition. This is kind of the trajectories of the fluid dynamics. So here we can see that we can see this oscillatory behavior in the anchor function. Okay, and why this fluid dynamics is useful, because so this dynamics is basically some systems of ODs pasted together. So we call every such so each of these components are basically smooth paths, and we can show that like as delta goes to 0, the actual algorithm operating with random samples, in the dynamics of that algorithm, we see this exact phases, and we can prove that like as delta goes to 0, the algorithm also behaves like the fluid dynamics, and it exactly converges to each of these phases. And since the algorithm closely follows the fluid dynamics, it also stops at the optimal allocation. So this is a summary of what I presented. Like, so first I introduced the best term identification problem, and then we studied the lower bound of the problem, and then using the lower bound problem, we did something called a track and stop algorithm, which is, even though it is optimal, it is like computationally very expensive. And to get rid of that, we introduced the clairvoyant anchored top to algorithm and studied its fluid dynamics. And using the fluid dynamics, we kind of sketched the proof that why it is asymptotically optimal. Yeah, thank you.
Any questions?
You get in the track and stop versus the clairvoyant algorithm?
So in track and stop, you have to solve this k-dimensional problem at every time, right? This constrained k-dimensional convex problem at every iteration. In in top two, you don't have to do any of that. It is just a order one. It is just a order k computation. You just have to compute this anchor function, and that's all.
So it's exponential in k versus linear?
Yeah, I'm not sure if it is. I mean, one also needs to consider like how well we are. If we are solving this k-dimensional problem, like we are not exactly solving it, we are getting an approximation of the solution. So one needs to consider all of that. I see. I see. Yeah.
I don't know which one of you should answer this.
Yeah. So I mean, so there are methods where they use this Frank-Wolf-based methods to they solve an LP instead of this whole convex problem, and those are also provably asymptotically optimal. But the thing is, we don't want to solve something at every iteration, and so that is what we want to get rid of. Yeah. No, even in the experiments also, when we measured the time, then also it is better. Yeah.
I had a clarification to ask about fluid dynamics
Yeah.
analogy.
Yeah.
Is it just analogy, or what would I have lost if I said it is a set of ODEs? Why mention fluid dynamics? For example, there are several ODEs which come special to fluid dynamics. Are you
Okay.
using any of those tools, or just
No, nothing like that.
Oh, so it's just a ODE?
So yeah, I mean, we can also call it a fluid OD. I mean, we use the word fluid because I mean, it helps us to explain.
But you are unable to exploit the techniques from fluid dynamics.
Yeah, no, not the classical like fluid dynamics. Yeah.
Thank you.
Yeah.
Let's thank this speaker again.
Wait a second. So, okay, it's time for lunch, but here at a